this video, we'll study machine learning component framework in detail. We have already talked about machine learning framework couple of times in this course. First, while talking about teaching philosophy of this course, and second time when we were trying to solve the problem of handwritten digit recognition with machine learning. There are 5 components in all in the component framework. First is the training data, second is the model, third is the loss function, fourth is the optimization procedure, and fifth is the evaluation criteria. To begin with, what we will do is we will list down or we will depict all the components of the framework and try to understand how they interact with each other. So on the screen, what you see is a diagram which has got the 5 components of the framework and their interaction with each other. The first component is the training data. You have data that is coming in from here and the label. So label and the data forms the training data together. Then we have model. Then we have loss function, then optimization procedure, and then the evaluation criteria. So any machine learning algorithm you can express in terms of these 5 components. So in that way, this is a very powerful tool for you to understand any machine learning algorithm. All that you have to do is whenever you come across a new machine learning algorithm, you have to ask 5 questions. What is the training data? What is the model? What is the loss function? What is the optimization procedure used to train the model? And what is the evaluation criteria? If you ask these 5 questions, the machine learning algorithm will be clear to you. And there are 2 phases in any machine learning algorithm. Those 2 phases are called training and inference. So you can see training marked with a green box and the inference is marked with a brown box. So during the training phase, the weights or parameters of the models are estimated, and in the inference phase, we take the trained model and use that to predict label for the new data. So we start with training data. Without training data, we cannot train machine learning model. So training data has the training examples and labels. So training examples are represented with a bunch of features. Now what we do is we also define a model, or we fix a model or a mathematical function mapping the features to the labels. But we do not know the weights of the coefficients or the parameter vector. So what we do is we start by assigning random weights or random values to the coefficient or to the weight vector, and what we do is we use that particular model to predict the label on the training set. Then what we do is we take the predicted label and we take the actual label, and based on that we calculate the loss. This is the loss that we incur for setting up the parameter vector to the specific values. Then we use this particular loss and calculate a parameter update in the optimization procedure. So optimization procedure yields us a new set of parameters. These new set of parameters are obtained by updating the old parameters. So we take these new parameters, so we have a new model effectively, and we again apply it on the training set. We again obtain new set of predicted label. We compare them with the existing label and the cycle continues. So we keep doing this until we reach an optima in the loss function space. So this is the point where the loss value is minimum. So if we can reach this particular point, we have a model or we have a set of weight values that minimize the loss. So as soon as we reach that point, we stop training the model. Sometimes what happens is it's very hard to reach that particular point, the minimum point. So in that case, we have another stopping criteria where we stop the model after few iterations. So we first define a set of iterations. We define how many iterations we want to keep repeating this cycle, and once the number of iterations are over, we essentially stop training the model. Then we are left with the weight vector of the model after the last iteration. Okay. So after training the model, what we have is we have a model with trained parameters or a weight vector. We use that particular model to make predictions on the new data in the inference phase. So in the inference phase, what happens is we input the data, we apply the model on that, and we get a predicted label. What we can also do is we can also calculate the matrix or the metric of evaluation based on the training set. So we can take a training set and apply the model on it, get the predicted label, and compare the predicted label with the actual label and calculate value of the metric. Okay, so I hope it is clear to you what are the 5 components and how they interact with each other. Now what we'll do in the remaining part of the video is we'll go through each component in detail and we try to understand various aspects of these components. Okay, but remember again, and I'm stressing this again and again, that this is a very powerful tool in your toolkit, and it will help you to understand any machine learning algorithm if you list down these 5 components of that machine learning algorithm. Okay, so let's look at each of the component in detail. So there are in all 5 components, as we have seen: training data, model, loss function, optimization procedure, and evaluation criteria. Let's look at the first component, which is training data. So remember, no training data, no machine learning. So we cannot do machine learning without having any training data. So training data is the must, right? So training data is the most important component of machine learning framework. In case of supervised learning, we have training data consisting of inputs and output pairs. Each input is represented by a bunch of numbers that are called as features or attributes. There could be some inputs which may not have features in form of numbers. So there could be inputs like images or text for which we do not have a numeric representation available readily. In that case, what we do is we apply certain transformations to convert the input into a bunch of numbers. Now you remember from our previous video of handwritten digit recognition, the training data there was the images of the digit and the label was the digit that was present in the picture. Okay, so the image was represented by a matrix of numbers and those were the features of the image, and then we have label also associated with the image. So as I said, if the input is image or a piece of text, we need to apply certain pre-processing steps or transformations to obtain feature representation for such input data. And we'll study what kind of transformations we need to apply on these type of data in this course. So as I said, each example is represented by a bunch of features, and these features are provided to us by domain experts. So for example, if we are solving a problem for predicting price of a house, the expert would tell us what features are important for determining price of the house. So the features could be number of bedrooms in the house, or the distance of the house from different utilities, okay, or it could be the total area of the house or number of bathrooms. There could be such kind of features which expert would know, and we need to consult them to obtain these features when we are constructing the training data. The expert would also provide us with data set of houses with their features and prices. And price is something that we are interested in predicting. The output in this case is a real number, which is a price for in case of house. It could also be a discrete value from a predefined set. The example of real value, as I said in the housing price prediction problem, output label is a price, which is a real number. The label could also be a discrete valued. So in case of handwritten digit recognition problem, we had 10 different values for class labels. So the image could be anywhere between 0 to 9. So image could contain digit anywhere between 0 to 9. If we take another example that we studied in the very first video of this course, which was of loan sanctioning, we said that banks use machine learning for determining whether to give loan or not. So for loan sanctioning, we have binary label. Loan is either given or not given. So this is a binary label. So there are two labels, 0 for loan not sanctioned and 1 whenever loan is sanctioned, or yes or no. So there are essentially two labels. So once we have obtained training data, we get an idea about what is the input and what is the output. So the nature of the output helps us to decide what kind of machine learning model would be suitable for the particular problem. And it also helps us to choose appropriate components like model, loss, and optimization procedure for training. So the second component is model, and model is something that provides the mathematical form of mapping between input and output. We had studied or we had looked at the linear form or linear model in our previous video. So the input is represented by a bunch of features, and output can be a real number or discrete value from a finite set. So the model will provide a mapping between the pair of input and output. So model is nothing but a mathematical formula. So one example of model is a linear model, which we also saw in the previous video. So here the output is linear combination of features. So output is equal to weight 0 plus weight 1 into feature 1 plus weight 2 into feature 2 plus and so on up to weight m into feature m. Of course, the features are known to us, but weights are not known to us. So the key problem becomes the estimation of the weights. All weights together form an entity that is referred to as weight vector. We need to estimate the weight vector by training the model on the training data. The ideal weights are the ones that when we use in the model, they produce output that is close to the actual output. So ideal weights are the one where model produces the result which is closely matching to the actual result. Again, as said earlier, depending on the nature of the output, we choose our model. When the output is a real number, we choose models of regression, which is capable of producing a real valued output. When the output is a discrete value, we choose models of classification, which can produce a discrete quantity as an output. The third component of the model is loss function, and loss function helps us to estimate the weight vector in a principled manner. So what exactly loss function does? So loss function figures out, or loss function provides a suitable method for measuring the difference between predicted and the actual output. And loss function is a function of weight vector, right? So as we change the weight vector, we obtain a new model, and because of new model, we get new prediction that leads to a different value of loss. Because remember, the loss helps us to measure the difference between predicted value and actual value. So we will denote loss with letter J, and J is a function of weight. So it provides a mapping between weights and the loss value. So loss is a real number. So J is a mapping from weight to a real number. And J of W is a difference between actual and predicted output for all training sample. The exact form of loss will differ from model to model, and we will study various loss function in this course. In the example linear model that we saw, we know all the features, and what is not known is really a weight vector, which is colored in red. So all these values of weight 0, weight 1, weight 2, all the way up to weight m, they are not known to us, and our job is to estimate these weight values based on the training set. In other words, we can change weights to get new model, and that new model would lead to a different result or output that would in turn result into a different loss value. So the example of loss function is a squared loss function for linear model. It calculates the sum of square of difference between the actual and predicted value. So I would like to clarify a bit about notation here. So this is predicted superscript I, and this I is not the power of this particular number, but we use this particular value of I to denote the index of the example. So this is the predicted value for the ith example, and this is the actual value for the ith example, and we are calculating the difference between the predicted value and the actual value, and we are squaring it up, and we essentially sum the square of the difference across all the training examples. So if there are n training examples, we essentially sum the square of the difference for all the examples, and that essentially is the loss function in case of squared loss. Okay, and now what we can do is we can simplify this equation by substituting the formula for predicted from the linear model that we saw in the earlier slide. So what we are doing here is we are substituting the formula for the predicted value with the linear model here, and you can again note that the feature value is the feature 1. This is a feature 1 for the ith example, the feature 2 for the ith example, and this is feature m for the ith example. So there are m features for each example, and what we are doing is we are essentially calculating a linear combination of these features to obtain the predicted label. Okay, so linear combination of features of ith example gets us the predicted output for the ith example, and then we are subtracting the actual value of or actual output of the ith example, and we are taking the square of the difference and summing it up as we have seen over here. So all that we do is we just take this linear combination and substitute in place of the predicted. Our job is to find a weight vector that results in the lowest loss as per the defined loss function. How do we estimate such a weight vector? Maybe a brute force way, but that is not sufficient. Brute force approach does not work because it is a combinatorial problem and it explodes very quickly. So what is the best way to estimate such a weight vector? Well, that is the purpose of our next component, which is optimization procedure. And optimization procedure provides us with a very principled approach for estimating a weight vector from a given training set, model, and the loss function. So we want to obtain a weight vector that minimizes the loss function. So we write that formally as follows. So we want W such that W that minimizes the JW. That's why we use this sign, we use this function called argmin. So you want that value of W that results into minimum value of the loss function. So here we use applications of derivatives that we study in 12th class, right? In 12th grade calculus, we have a section called applications of derivative, and that will come handy in this particular, while solving this particular problem. So what we do is we essentially take derivative of the loss function with respect to the weight vector and set it to 0. So we write ddw of the loss function and set it to 0. We solve this equation directly or with analytical methods to obtain the optimal weight vector. The optimization procedure is a cornerstone of model training. Now, the last component of the machine learning framework is evaluation. So, after optimization, we essentially get the final model, the model with optimal set of parameters or weights. So, the problem becomes how do you evaluate whether the model is good enough, right? So, we typically evaluate the model on unseen data. We do not use training data for evaluating the model because that would not give us the correct estimation of the goodness of the model. So, what we do is we set aside some data from the training set as a test set, and we evaluate our model on that particular unseen data or on test set. So, the key question becomes, what metric should we use to evaluate the model? And again, this evaluation metric changes as per the problem type. There are different metric for regression and classification problem. So, remember, regression is the one where output is a real number, and the classification is the one where the output comes from a discrete set. So, after evaluation, we essentially obtain the metric that denotes the performance of the model. What do we do if the model does not perform as per our expectation, right? So, we need to do something about it. So, we typically reiterate the machine learning pipeline by trying to add either superior features or using a superior model or loss function or optimization procedure. And this cycle continues unless we get a satisfactory model. So, let us summarize the machine learning process. So, there are two phases in any machine learning process, training and inference. So, you take any machine learning algorithm, it will have two phases, one is training and second is inference. In the training phase, we try to estimate the parameter vector or weights of the model, right? So, we have to essentially fix the model ourselves, and that model will have bunch of parameters, or it will have a weight vector, and we need to estimate that, and we estimate that weight vector using the training data. Training data is a pair of examples and labels. Each example is represented by a set of features, right? So, we take the model and we apply that model on the training set, we get a predicted label, we compare the actual label and predicted label and calculate the loss. And using the derivative of the loss in the optimization process, we obtain a weight update, we obtain a new set of parameters, and that gives us a new model or a model with updated weight values. And again, we apply that model on the training set, obtain new predictions, compare it with the actual prediction, and the cycle continues. So, once we have optimal set of parameters, either the optimization algorithm reaches to the optimum value of the loss function, or after we exhaust the set number of iteration, we get a model with final set of parameters, and we can use that model to make prediction on unseen data. And so there we will get predicted label as an output, and we can also calculate the performance of the model on unseen data as well as training data. We can also calculate that performance with predefined or with pre-selected metric. So that's it from this video. I hope you got a good idea about machine learning framework, and you got to know different components of this framework in more detail, and now you are familiar with two phases of any machine learning algorithm, and you now have a tool that can help you decode any machine learning algorithm by listing it down in terms of these 5 components. I hope you enjoyed this video. We will see you in the next video. Until then, namaste.